Okay, on Chapter 5 test, some of you did not read the directions, and so I'm going to read them to you so that you understand what I'm looking for here. We have studied the finding integrals by these methods: substitution, parts, partial fractions, trig substitution, and tables. You must show your proficiency in using these four methods: parts, partial fractions, trig sub, and tables. Notice substitution by itself isn't in here, and there's only four of them. So you need to show, using one of these four of these five problems, you need to show that you know how to do parts, partial fractions, trig sub, and tables. Not just figure out the answers. You need to show me you know how to do those methods. Okay, so let's talk about those methods. Now, for me, my personal preferred is to look for ones that can be done with partial fractions, because that needs some very specific things. Specifically, it needs to be able to factor a denominator. So first of all, there's only three of these that have denominators in them. This one, the denominator does factor, but it's got a square root. It's 3 has power, which is square root. Partial fractions, we don't deal with square roots when we're factoring. This one is a possibility, but it's x squared plus 9 and no other factors, and x squared plus 9 does not factor. So it's out. It's out. So it has to be this one that we're going to do the partial fractions on. And x cubed minus 4x factors. Now, if you don't know how to factor it, you can turn on a calculator. We can go to y equals and clear, and we can type in x to the third minus 4x, and then we can graph, and it crosses at minus 2, 0, and 2. The factors must be x plus 2, x, and x minus 2. Now, some of you tried factoring x squared plus 9. If I type in x squared plus 9 and graph it, you don't even see it. If I go to zoom 6, you'll see it barely up here. It does not cross the x-axis. Therefore, it does not factor. Now, you could type in the x squared minus 9, but when you have the it cubed and square root, you're not going to want to do that one. So this one factored to x, x plus 2, and x minus 2. Now, if you don't see how that happens, think about this. What can we pull out of this? There's a common x term in it, and that would leave x squared minus 4. And you should recognize x squared minus 4 factors to x plus 2 and x minus 2. So, this is the one we're going to do with partial fractions. Now, you might be able to do it with other methods, but you're required on this test to show me that you know how to do partial fractions. So this is the one you can do that on. The next one is, I prefer to do, is a trig sub. To figure out which one to do with that. Now, to do trig substitution, you need to be able to have either on, you're going to make a triangle. Let's start with that. You're going to make a triangle, and if you put stuff on here, it's going to be the square root of that one squared plus that one squared. So it's going to be plus, and something squared plus something squared. So you want a quantity squared plus a quantity squared. If you're on one of these sides, it's going to be a quantity squared, the hypotenuse squared, minus the other leg squared. or if you put the x, and you could put a number on the hypotenuse, and so it'd be a number minus an x, and if the x is on a side, or you can have the number on a side and x in there and hypotenuse, so x can be here or here. The variables can be here or there. So we have to find something that either looks like something squared plus something squared or something squared minus something squared. Well, we got x squared minus 1, which is 1 squared. So this one could be done with trig sub. And this one's got x squared plus 9, which is 3 squared. So this one, it doesn't have a square root, but you can still do it. So trig sub could be done with this one or this one. Okay? Next one we want to talk about is integration by parts. Now, integration by parts is one where we do the table. At least I do the table. You can follow the pattern that they explain in the book, but I like to do the table. Now, let's talk about that. When we have we're trying to take the derivative of two things multiplied, like u and v. If we try to take the derivative of that, then we have to do the product rule. We do the derivative of u times v plus the derivative of v times u. Or if you will, if we had a and b, it's a prime b plus b prime a, or that ABBA thing that we talked about in Calc 1, if you were in one of my classes. So if we were to had to integrate AB, and it was the derivative of it, those would cancel, and we get AB, or UV, equals the integral of A prime B plus the integral of B prime A. And either one of these can be subtracted to the other side and leave you with either this or this on the other left alone. So when we're looking at these, we're looking for two things multiplied. One of the pieces is going to be a derivative and the other is a non-derivative. So looks like we have that case here and here where we have two things multiplied. Two things multiplied. Now sometimes the only thing that we have is like a dx. But of these two, the other thing is that when you do this, let's say I put u here or a here and v here or b here, and made a list of the function and its derivative. So one of the pieces is the function and one is the derivative, and I don't care which one you use. So over here, one of them is going to be the function, the other is going to be the derivative, and you're going to undo each. You're going to take the function and find its derivative, or you're going to take the derivative and find the function, do the antiderivative. If you are doing the derivative of one of these, you would like generally for the derivative to produce something simpler. So in this one, if you put x here, now notice, if I put x there, all the rest of it has to go in the other part, including the dx, has to go across. It's the derivative and the regular. So here's the regular, here's the derivative. So I'm putting the rest of it as the derivative of v. If I did this one, it's a little bit messier and something that we probably don't want to do. If I chose, for example, to put cosine squared x here, the derivative of it is going to be 2 cosine x times the derivative of cosine, which is negative sine. Negative 2 cosine x sine x dx. I don't particularly like that. And I'd have to integrate the other part, and the sine squared x dx is not a simple integral. So this is probably not one I want to do with integration by parts. This one doesn't look very appetizing, nor does this one. So this is the one we're going to do by parts. We put the x here, not over here, because we want to make it simpler when we take its derivative. And the derivative of x is 1 dx. If we're doing the antiderivative of this, well, see, if the derivative of sine is cosine, then the antiderivative of cosine is sine. So this is the one we're going to do by parts. Either one of these by trig functions. So that leaves this one, and hopefully we can find something in the tables for this, or this, or this. Doesn't matter which one. But we have to do trig on one of these, and then trig sub. So again, your goal is to demonstrate you know how to do these methods. And when I scored this test, the first thing I'm giving you points for is I'm looking for, have you demonstrated each of these methods? If you have, you get your 8 points. Or have you at least chosen correctly for which ones to do them on. Reasonable choices for each of these 4 methods. Notice you don't have to do 5 problems, only 4. Demonstrate the methods. And you didn't have to do the substitution. That shows up enough that it'll show up in the problems, and I'll know whether you know how to do substitution. So, now let's go to this first problem. Can we do this one with tables? So let me pull the tables out and take a look at the tables. In the tables that were provided, is there anything that talks about the square root in the denominator? Yes, here, but it isn't to the third. Not to the third, not to the third, not to the third. None of them are to the third. Probably not tables here. How about this one? Is there something that has x squared plus 9? Well, that looks like 15, but there's no x in the numerator or u in the numerator. Is there one that has that? And the reason there isn't one, it has u squared, but not just u. The reason they don't have that is because that one works really easily with substitution. How about cosine squared plus sine squared? Well, 11 and 12 have cosine squared and sine squared. So this is a great one to try to do something with using the tables. Okay, so now we've got our choices of this one or this one to show trig sub. So I'm going to do trig sub on this one. Let's see what we come up with here. So on trig sub, if there's a positive and negative parts. The negative is understood when you do the Pythagorean triangle. So you're not putting negative 1 on the side. You're putting either the square root of this, which is 1. You're putting the square root of that term on one of them. And if this is the positive part and the negative part, the positive part has to go on the hypotenuse, because you do the hypotenuse minus the leg squared. So x has to go here. And 1 has to go either here or here. And it turns out we like to put it here, but some of you put it on the other one, and either way works as long as you're really careful. So the first thing is you make the triangle. Now what happens to be this side? Well, according to Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. So the hypotenuse squared minus a leg squared is the other leg squared, if you take the square root. So we got x squared, the hypotenuse squared, minus a leg squared, minus 1 squared, which is 1, and then square root is the other leg. That matches this. Now, this said, and some of you got tangled up with this, it says to the 3/2 power. Well, the half makes it a square root, and the 3 makes it cubed. So it has the square root. It has this. So there's only two things I need to replace in this one, the dx and the square root. So I have to have an expression for x. And I want to put it in the numerator. Now some of you called it 1 over x's cosine. But we want the x to be in the numerator. So if 1 over x is the cosine, I'll write it, but I wouldn't have if I was doing this, then I would want to do the reciprocal, and so I need the reciprocal of cosine, which is, so the secant, which would be x over 1. Okay, so this gives us a value for x. You want a value for x. You want a value for dx, because we have dx. So what's dx? Well, we take the derivative of both sides, and some of you were sloppy. Derivative of secant of theta is secant theta tangent theta, but you're taking the derivative, so it's d theta. If you leave it out, you're going to get confused, and the x becomes, this is 1x, or x over 1. It's the derivative is 1 dx. So we have something we can replace x with, something we can replace a dx with, and then we need something to replace the square root with. So the square root would be, I can go opposite over hypotenuse, that would be sine, but it would have an x in it. I don't like that. I could do opposite over adjacent, and that would be tangent. So the tangent of theta is the square root of x squared minus 1. So now I have something for the square root, something for the dx, and if I had an x, I have something for the x. So now I go to replacing things. I have the dx. That's secant theta tangent theta d theta. All of that for the dx. I have the square root, which is tangent theta, and it's in the denominator. And that square root is cubed, so I have to cube the tangent. Okay, so now I have to try to simplify this a little bit so that I can do some integration. So this tangent will cancel one of the tangents, and I'll have the integral of secant theta, that tangent cancels 1 over tangent squared theta d theta. Now, I've done my trig sub. I could go look in the tables for something, but you're not going to find anything in the table that will really help us with this. So we have to remember our trig from 154. And one of the things often is done is gone to the sines and cosines. Now, you don't have to. There's other ways to do this, but secant is 1 over cosine. And tangent, 1 over tangent is cotangent, and cotangent is cosine theta over sine theta. But the tangent is squared, so I got to square these. And then the square will cancel one of the cosines, so I have the antiderivative, the integral of cosine theta over sine squared theta d theta. I could move the sign up and call it cosecant squared, or I could call it sine to the -2 and use a table formula, but substitution works on this one. If you're familiar with substitution, the derivative of whatever we let u usually ends up in the denominator, canceling the numerator, and that would be derivative of sine is cosine, so it would cancel the cosine. So if you let u equals the sine of theta, du would equal the derivative of sine is cosine theta d theta, because it's a derivative of the inside. So this becomes the antiderivative of cosine theta. We're not replacing it. We have sine in the denominator, so and that's u squared, and d theta is du over cosine theta. The cosine thetas cancel, and we have the antiderivative of 1 over u squared du, and that's the same as the antiderivative of u to the minus 2 du. And when you do antiderivative of power, you add 1 to the power and divide by what you got. If I add 1 to minus 2, I get u to the minus 1 divided by minus 1 plus c. Well, divided by minus 1 is the same as minus, so I've got minus 1, and u to the minus 1 is 1 over u plus c. And u was the sine of theta, so I have minus 1 over the sine of theta plus c. And now to get back to x's, look at the triangle. Sine of theta is that divided by that. So we'd have 1 over this divided by that, or since it's 1 over, it means reciprocal. It could be it's minus x over the square root of x squared minus 1 plus c. So that's the trig sub on that one. Now we could have done trig sub on this one, so I'm going to go to it and do trig sub on the x over x squared plus 9. This one is really easy to do with substitution. You'll let u be x squared plus 9, and you can do it. But I didn't ask you to show me using the u sub. I want you to show me that you know how to do trig sub. So first thing is you draw your triangle. Both of these are positive, so either one could go on the no. Both of them are positive, so we're not subtracting. So neither one of them is a hypotenuse. Together they make the hypotenuse. So we have to put x on one side and 3 on the other side. Square root of this, square root of this. So I can put x here or here. Doesn't matter, but it turns out it's a little easier if you do it this way, so that we get x over 3 is the tangent of theta. And the hypotenuse is leg squared plus leg squared, either way. So this is x squared plus 3 squared, or 9. So the tangent of the angle is x over 3. So x is equal to 3 tangent theta. I've got an expression for x. I need an expression for dx, so I'm going to take the derivative of this. And so we get 3, and the derivative of tangent is secant squared theta d theta, and the derivative of 1x is 1 dx. Need to have the d theta and the dx in it. So I have an expression for x, an expression for dx. Now I need an expression for the square root. Now I can do the square root with the 3 or the square root with the x. I don't want to make this any more complicated than I need, so I'm going to do the square root of 3, this with the 3. So that would be, and I want this in the numerator, so that'll be hypotenuse over adjacent, which is the reciprocal of cosine, or secant of theta is the square root of x squared plus 9 over 3. So I don't have the square root completely. I got a 3 there, so I'm going to multiply both sides by 3. Okay, so now we have all 3 of them, so we can substitute do our trig substitutions here. So what's the x in the numerator become? Well, x is 3 tangent theta. What's the dx become? Let's see, that's 3 secant squared theta d theta. What's the x squared plus 9 become? Well, the square root of it is this, so I'd have to square both sides to get that. So it'd be 3 secant theta quantity squared. Now let's simplify. So I got 3 and 3, and then I have 3 and 3 here because of the square. So all the 3's cancel. So there's no constants. Now I have a secant squared and a secant squared, so they cancel. So all I have left is tangent of theta d theta. I've done the trig sub to get to here, so now I can use tables if I need. And I look at the table and it says the antiderivative of tangent is a natural log of secant of x. So natural log, absolute value of secant theta plus c. And the secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is the hypotenuse over the adjacent. So this is ln absolute value of the square root of x squared plus 9 hypotenuse over adjacent, which is very close to looking like what you would get if you did substitution. If you do substitution, you get something that looks like ln of square root of x squared plus 9, or 1/2 the, well, I'll continue here. But if you got a division, this can be called ln of 3 plus a constant. Well, this is a constant, so those could be combined, so you can ignore that. And then this is the half power, and you could pull it out, and you can call it 1/2 ln absolute value of x squared plus 9, which is what you would get with substitution. These become a new c, a different c. I'll call it c2 or something. And the square root becomes out as a half. So that's how this and the answer you get from substitution match up if you did it with substitution. Okay? So, we've done one of them. We've talked about trig sub. Let's go to the partial fractions. Now, I already told you that we've already looked at that. That's this problem, so I'm going to flip through, get the last one. And here we go with this. Now, this denominator, you pull out an x, you get an x times x squared minus 4, and that becomes x times x plus 2 times x minus 2. They're all linear factors. They're all different. Now, some of you did it with this, and this, and it is possible to do that. This is a quadratic factor, and you have to do bx plus c, a over this, and bx plus c over that. But they're all linear factors. If you can get them to linear factors, a lot easier. It becomes the integral of a over one of them, I'll put the x there, plus b over one of them, I'll do the x plus 2, and then c over one of them. So we're trying to turn this fraction into these three fractions, something that's equivalent to that. All right, now some of you had trouble with what do I multiply by? Well, if a is here and has an x, it doesn't have these two. So I need to multiply those two. Well, we know those two multiply to be x squared minus 4. B has the x plus 2, so it doesn't have these two. So I have to multiply these two, which is x times x, x squared. X times minus 2 is negative 2x. And this one has the x minus 2, it doesn't have these two, so I have to multiply those, and that becomes x squared plus 2x. Now there's lots of different ways of doing this solution. I chose, not the way the book does them, is to just say, okay, look at the x squareds. It's got to be identically equal. There's no x squareds in the numerator here, so 0 has to equal. We've got ax squareds, bx squareds, and cx squareds. Then I look at the x's. There's none over here. Over here, a times, there's no x in that, so I'm not going to get a times any x's, but I do get minus 2x's times b, so minus 2b, and c times, I get 2x's there, so it's plus 2c. And if I look at the constant, I have a 3. Here I have a times negative 4, so negative 4a. There's a constant. There's no constants here, and there's no constants there. So right away I see that a has to be, since this is a very simple equation, has to be 3 divided by negative 4. Negative 3/4. This is telling me, if you divide everything by 2, that b and c are equal, and if a is negative 3/4, b and c have to be 3/8 each. Half 3/8 plus 3/8 is 3/4, plus a negative 3/4 is 0. This is telling us that b and c have to be equal. You could also take this equation, put the negative 3/4 here, and divide this one by 2, and it would be 1b and a minus 1b plus c, and you could add it to this, and you would get negative 3/4 equals 0 plus 2c. Add the 3/4, divide by 2, and you'll get 3/8 for c. And this is saying b and c are equal, or you can plug them back into there, but you end up with this. So, now to do the integration. This becomes the integral of negative 3/4 over x plus the integral of 3/8 over x plus 2 plus the integral of 3/8 over x minus 2. If you factor out the 3/4 on this, you get minus 3/4 integral of 1 over x dx. 1 over x is ln x, the antiderivative, absolute value of x. Plus, if you do a u sub on this, let u equal x plus 2, du equals dx, and so this becomes, you can pull out the 3/8, and you have the derivative of 1 over u du, which is 3/8 ln of u, but my u is x plus 2. And the same kind of thing here, if you let u equal x minus 2, du equals dx, and so this becomes 3/8 integral of 1 over u du. So it becomes plus 3/8 of ln absolute value of u, which was x minus 2, plus c. Since these both have the same coefficient and they're added, a log rule says that can become 3/8 times ln of these two multiplied, which is x squared minus 4. This one doesn't have the same coefficient, so you can't quite do that. There is something you could do. So this is another valid answer, which is what you can get if you were to put bx plus c over x squared plus or minus 4. You get something that looks more like this. But now I've shown that I can do integration by parts, or by partial fractions. So I've done partial fractions, and I've done trig sub twice. Now we need to go and do the other two methods. All right, so integration by parts. This looked like the one by parts, which is this one. So let's go down and do it by parts. So we have one of these has to be the derivative, and one is the antiderivative. The derivative will go with the dx, and I'm going to have to integrate it, and the one that doesn't go with the dx, I've got to take the derivative of. Well, I just as soon take the derivative of x, so I'm going to put in my u the x, so that when I find its derivative, I get 1 dx. Then the rest of this, all the rest of it has to go in the derivative, which is cosine x dx, and then I have to take the antiderivative to get back to the function for v. And so that would be, the antiderivative of cosine is sine. So this is what I expected you to lay out. Now, if you do it with just the formulas in the book, you can do it. But now we broke this up, making these two boxes. This is the u v prime. Now in the formula, it's u v prime and v u prime. So this is what we've got to integrate this way. Those two. But there's also the u times v, which is x sine x minus the integral of the opposite of what we laid out. If this is v prime and that's u, then we have to do the reverse of them in here, which is sine x times 1 dx, this way. And the integral of sine is negative cosine, so we get x sine x minus negative cosine x plus c, so we get x sine x plus cosine x plus c. And that problem is done. And I've shown that I know how to do the integration by parts. Now we could also do it by using, I just want to say that usually if we have a number, an x or an x squared or an x to the third, and something that doesn't reduce, just changes like cosine to cosine, or e to the x stays e to the x stays e to the x, we usually let this be the u, and then take the derivative of it, and the rest be the dx, the derivative and antiderivative of that. There is the one exception, and that's if we had ln x in it. And even if it was x squared ln x dx, I do not want to put the ln where I have to integrate it in this formula. There may be times when you have to, but seldom. Usually you'll put this in the u spot and the x squared here with the dx, the x squared dx here and work them. So the ln is that an exception to the rule of usually putting the x in the u spot. Okay? All right, I'm going to stop the video here because I have to go to class, and then I'll continue on with the tables method and on this problem, and then we can go to doing the last of it. So